Okay, everyone. So finally get to Thomson 5.3, which is the introduction to quantum electrodynamics. So in the previous sections, in chapter 5, right, we learned that we can calculate these Lorentz invariant matrix elements, right? But what we did is that we assumed that, well, we made it so simplified it by making these a scalar particles, right? And what that allows us to do is just say that, well, the matrix element is just going to be, right, proportional to these coupling constants GAs and GB, where each of these is like the vertex in each of the interactions. But we know that the electrons are not scalars. Just to clarify, scalar particles mean it's a spin zero. Okay, there's no spin in that particular particle. Okay. For electrons, right, we know it's spin 1/2. Actually, if we're following the Dirac Hamiltonian, it has to be a spin 1/2. Otherwise, there'll just be an unoccupied state that doesn't make any sense. And photons, in case this is something that may have skipped in your electricity and magnetism class, is actually a spin 1 particle. Okay, it's a integer spin of 1. So how do we deal with this? Okay, so in general, we can't just sub in these GAs and GBs in the transitional elements. Okay, so this may be GA, this may be GB, right? So we actually have to make this calculation. So how do we deal with this? Okay, how do we find this stuff? The propagator is the same. In fact, for quantum electrodynamics, since the particle being exchanged is a photon, the mass of a photon is 0. So therefore, it even simplifies quite a bit. So without this mass term here, okay? So for example, if we were to scatter an electron off a tau, right? So you have a E minus here, a tau 0, a tau minus here, right? They both are negatively charged, so when they come close together, they will bounce off each other, okay? And in quantum electrodynamics, this is done through an exchange of a photon, okay, which is the symbol gamma here, okay? So these are the particle names, right? Tau, tau, E, gamma. On here, they also label P, the momentum of particle 1, momentum of particle 2, momentum of particle 3, momentum of particle 4, momentum of the particle being exchanged, the photon, okay? This is make sure this is not confusing, because this mu here is actually the Lorentz index. Mu equals going to be 0, 1, 2, 3. Okay, it doesn't mean the muon, and the nu here doesn't mean neutrino. It's also an index of 0, 1, 2, 3, 4. Okay, it's just an indexing. Okay, I don't like that he does this, but that's what he decided to do. Okay, so how do we deal with two particles scattering off each other? Okay, so in classical physics, right, if a charged particle interacts with the electromagnetic field, this is actually described in a little bit more detail in this optional section 4.75. I think you shouldn't need to read through that. If you want to, you can. But what we want to take out of this is that the electromagnetic field can be described as these vector potential fields, okay? In fact, it's actually also a 4-vector where the first one is named phi, and phi is just the electric potential. So basically in your electrodynamics class, this will be denoted as V instead. So they use V, phi. Okay, now I'm sounding like, a giant or something like that. But anyway, so instead of using V, because they didn't want to use V for the potential, because we use V for potential energy in particle physics, they used phi for the electric potential. Okay. And then this A here, this A stuff, okay, the A stuff is actually the magnetopotential, and you may not have run into this until you take the upper division electricity and magnetism class. It's actually in Griffith's chapter 5, where he deals with the magnetic potential. It's basically the potential energy stored if you have a charged particle in a magnetic field, okay? And it's defined as just the cross product of this potential equals to B, okay, the gradient cross product of this potential equals to B, okay. So we're not going to go through all the mathematics from section 4.75, but the main point here is that in order to account for the interaction of electromagnetic field, meaning putting the photon inside this diagram, okay, what we need to do is we basically have to change the covariant derivative from its original form to I, well, the imaginary number, right, times the charge times the covariant electromagnetic field potential. Okay, so up here it was defined by as the contravariant, where we can just lower the index into the covariant, where we're just basically switching the sign of the A. But yeah, but I'm not going to go through all the mathematics in here. But this covariant electromagnetic field, right, can be written out actually as some polarization state, and I'll describe what that is. And then since it's an electromagnetic wave, so it's also a wave, so it's just EI P dot X minus ET, which is just a wave function, right? Sines and cosines. Okay, so there is this polarization situation going on. In general, there could be a normalization also, but that normalization is actually usually absorbed into the fermions. Okay. So what is this epsilon thing? Okay. So epsilon mu, right? Since it's mu, right, it's also a 4 vector. Okay. So there'll be 4 components to it right away. As soon as you see a Greek letter mu, if it's not a muon, then it's a 4 vector. Okay. Right. And then there's also another index here, lambda. Okay, lambda not for the wavelength, lambda as in the polarization. Okay, it's just this one I can't blame Thomson for, but this is the notation that basically all of the particle physics field uses. Okay, so for a photon whose electric field, right? So remember when you have a photon, let me draw that actually, right? Let's say it's going along the z direction. You have your x and your y's, right? So some electromagnetic wave will have its electric field polarized along the x direction, and then the magnetic field, right? The magnetic field pointed, right, in along the y direction. And by convention, okay, we pick the electric field to be the direction of the polarization. Okay, so if the polarization is along the x-axis, this 4 vector, right, you can use right in the mu or not, right, it's going to be the first polarization index 1, and that's going to be polarized along the x direction. So remember, this is time, x, y, z, okay? The rest of the components are 0. If the electric field is polarized along the vertical direction instead, okay, or the y-axis, okay, what we're going to do is we just have this polarization 4 vector, right? But then we put the 1 in the y component instead, okay? We're not going to have to deal too much with this, but it's just important to know where this epsilon thing comes from, okay? Even though the particle is spin 1, remember spin 1 particle in general, right, can have spin 0, can have spin +1, can have spin -1. But for a massless particle, it's actually not possible for it to have any polarization along the direction it's traveling. So the polarization along the z direction cannot happen. So therefore, you actually only have 2 polarization. Okay. All right. So the Hamiltonian for a spin 1/2 particle in a electric potential. Okay. Well, let's just talk about it before we add in the electric potential. Okay. So the Dirac Hamiltonian used to be, right, this negative I gamma not gamma 0, and then there's this gradient thing, okay, and then plus m gamma naught, right? And that's acting on the wave function. Okay, so essentially what happens is that if we put this particle in a electromagnetic field, we're going to add this second piece here. Okay, where the second piece came all the way from up here, where you have this additional partial, this covariant derivative changing from just the regular covariant derivative, but with a IQ A mu. Okay, okay. And then you have the Q here. The I actually kind of canceled out because you also have another factor I. Okay, and this gamma mu here is just to deal with the fact that your things are spinors. Okay, the fermions are spinors. Okay. Okay, so it's kind of like adding this, a mu to this. Okay, and then having another term. All right, so this is the Hamiltonian if the fermions are interacting with an electromagnetic field. Well, and itself, of course. So I just described, right? The first term is just the good old free particle Dirac Hamiltonian. The second term is the one that is the contribution from the electromagnetic field. And this is the one that we're actually concerned with because this kind of acts as like a potential, right? This is a potential, right? Remember when we did regular Hamiltonian, a lot of times we just kind of ignore, right? So this is the non-relativistic Hamiltonian, right? It's like p squared over 2m, but then you add a potential term to it, which is, some sort of potential energy. So since this part basically acts as this first half, okay, this part acts as the potential. Okay, that's the analogy I want you guys, the connection I want you guys to make. Okay, so what we're going to do is we're going to define this Dirac potential, okay, and this Dirac potential is just a copy of this, right? Q times gamma 0, gamma mu, times this, well, contracted, right, using the Einstein summation contraction convention, right? This will be actually, it has no mu on the other side because whenever you have mu, you have just gamma 0, A0, oops, right, plus gamma 1, A1, plus gamma 2, A2, plus gamma 3, A3. That's what this represents, okay? So what we're going to do is we're going to stick this into our Lorentz invariant matrix element, right? So we're going to stick this VD in here, okay? So Thompson doesn't go through all the math, so I'm not going to do so also because that just turns into a lot of like e to the minus I px, canceling out and stuff like that. But the main thing you want to think about is that, well, this wave function on the left-hand side, right, just kind of turns into the spinor, right, just as in the scalar case, right? Okay. Similarly, the wave function on the right-hand side, right, turned into a spinor part of the on the other side. Okay, so just be careful not to reorder things unless we know that they are commutative, right? Right, and this VD, okay, this is the stuff in the middle here. Okay, VD, let's describe this one at a time. So there's a Q here. So why isn't there a lowercase q here? The lowercase q there got replaced by Q times E, right? QE times E. Yeah, I love this notation, okay? So Q is equal to Q sub E times E. E is the electron charge, okay? So, in SI units, this will be 1 times 10 times negative 19 Coulomb. But in natural units, there's a different formula to figure that out. So we'll do that later, okay? And this big Q either represents +1 or -1, indicating the charge of the particles we're dealing with. If we're dealing with electrons, then this will be -1. If we're dealing with positron, this will be +1. That's the only difference. Okay. The rest is a copy down, right? Oops, if I can go to, let me maximize this actually. Wish I can have more markers, more highlighters, right? Gamma mu, gamma 0, gamma mu, right? That's the same thing as down here. And then A mu, right, got replaced by epsilon mu, okay? right? Because, right, epsilon a mu is this times this, but then, you know, all these e to the IPX stuff cancel each other, basically multiplies to 1, right? Because all the exponent multiply adds up to 0. Okay, so that's the interaction piece of within the Lorentz invariance matrix element that we're going to plug into, right? The goal was to figure out, let's go all the way back up here, right? To figure out what this stuff is up here, right? Okay, and that's what we're trying to write out. Okay, so that's what this equation, where is it? Where'd it go? Oh, sorry, here. This one is. Okay, so this deals with the vertex of whatever P1 and P3 is with the photon. So this only deals with this top half, right? So you have an electron coming in, right? The electron going out. This label P3, and then you have a photon coming out. That's what this is. Okay, this part of the diagram. Okay, all right. And this lambda, right, actually runs from lambda equals to 1 to 2. So essentially, you basically have 2 of these diagrams, okay? Right, one for lambda equals to 1, one for lambda equals to 2, okay? You have the vertical, and then you have the horizontally polarized photons interacting with this. All right, so for the second vertex, right, so let me draw the bottom half here, right? So you have P2. I think this is a tau this time, right? P4 going out, okay? And then this is accepting a photon, right? This vertex here, okay? You do something very similar, okay? So you have same thing here, right? Where you have the spinner part for, let me highlight the right stuff, right? The spinner part for the incoming part, for the outgoing particle, okay? Right? Okay? And then the incoming particle, right, has the spinner part here, okay? And I just want to now get you guys thinking about this in your head right now, right? Notice that, you know, if I'm reading this left to right, right, this is the last particle, right, that in the diagram. This is the first particle in the diagram, and this is the middle one, right? So whenever you have a Feynman diagram, you actually want to start from the end, start writing this from the end. This connects to this connects to this, and this piece connects to this, okay? It's kind of like reading backward, okay? Just sort of neat. We're going to see this when we find the Feynman rules, okay? Okay, so plugging all of this stuff in, okay? Remember scrolling all the way back up here, right? Plugging all this stuff in. Now we have the propagator, right? This little piece in here. The mass of the photon is 0, so this m of x is actually 0. So we're going to have to deal with the m of x at least, okay? Right? We plug in the left-hand side, the first diagram, the second diagram, right, from up here, right? That's from up here, okay? Right, okay. What we're going to do is we're going to put these little polarization factors, right, next to each other near the propagator, but it's not part of the propagator, right? The propagator is just 1 over q squared because the photons don't have mass. Because what you can do is actually, if we sum over all the possible all the polarization, sum over all these pieces. Let me just circle them in red so that's easier to know what I'm talking about. So we have to do this summation over lambda, and the only stuff that has lambda in it is these epsilons, right? Okay. If you sum over all these possible lambdas, this actually turned out to be the negative of the space-time tensor, okay? And if you want the derivation for it, you can actually either A, do it yourself, because what you have here is basically a 1/4 vector multiplied by a 4/1 column, okay? And this multiplication and summation basically turns it into a 4/4 matrix. But the neat thing is that it turns out to be negative this. So if you put a negative sign here, this just changes all the negative signs. So it changes the time component, the time-like component, to be negative. So this Lorentz invariant matrix element now becomes this long big thing, and then how do we deal with this? Okay, this is where we're going to do a few shortcuts just to make the notation a little bit easier to read, and this equation not quite long to write out. Okay, so remember from chapter 4, we defined this thing called the adjoint of a spinner, right? So therefore, right, whatever U dagger gamma 0, you can actually replace that with U bar, the adjoint spinner. Okay, so here we have that, right? And then here we also have that. So that reduces it a little bit. At least we get rid of one of the gamma 0. So with this substitution, you get the next equation, which is actually the book that highlights. And you know it's important because it's in this big gray box, right? So he wants you to notice it, and because we're going to use this equation over and over and over again. Okay. All right. Another simplification, which is additional steps, but it might hide a lot. Of like the information that you may want to just have it out in front of you, right, with all these factors, right? Is that what you can do? Is that you can rewrite this piece here, right? This U adjoint gamma mu, and then U of the incoming particle as a current, okay? So back in chapter 4, we also defined that the forward current, right, these probability density current, right, they are defined as, you know, some U, U dagger gamma naught, right, gamma mu, and then some U, right? You can also utilize that here to shorthand this equation. I'm not sure this is going to be super useful because it hides so much of this stuff, because we eventually have to deal with this momentum stuff anyway. Okay. So what you can do is then, well, wherever you see this, right, UE, gamma mu, UE, which is this part up here, right, you can substitute in this forward current, okay, of J of the electron mu, okay. So therefore, this turns out to be what's down here, okay. Similarly, for the tau, you can substitute in this piece here for the tau, okay. So the Lorentz invariant matrix element turns out to be, well, there's a negative sign in front, okay. And then, you know, if they are same charge, different charge, this will determine the signs of you know, QE times Q tau, capital Q's, right? You have the charge of electron, the elementary charge square, okay. And then you have the current divided by Q squared. This is a very short form and hides so much stuff. Typically, we actually want to stick with equation 5.16 in order to actually understand how to put in the values of P's and U's and the spinners, in fact. Okay. And I'm not sure why I typed 777 on the bottom, but so that's this section.